Cool. So, Amel talked about something, very ambitious and exciting, and this is going to have a very different tone. This is a kind of a feel-good story about why, programming language semantics and Coq are awesome, and how they can have an impact on the real world. So, in a sense, everything is in the title, even the first line of the title, CertiCoq-Wasm. That's it. Maybe I'll talk a little bit more about it. So this is joint work mostly by Wolfgang Meier, who is a master student, and then us. And if the title wasn't enough of a short summary, here is another short summary. So we have a way to turn Coq programs into WebAssembly programs, and it's verified. If I had wanted to be whimsical, I could even have put like another cockerel up there. So I won't run a demo because I've been scared with all the AV problems. But basically, the way you use CertiCoq-Wasm is you write your Coq program. For example, here, this definition foo, where you run super exciting mapping of odd onto some numbers. And they would like, but I would like to run this fast. So I'll just use CertiCoq to extract WebAssembly code into this foo file, and then I will call node.js, as part of my verified infrastructure, to run this very fast. Or at least, this is the whimsical version. The serious version is you take your Coq program, you extract it to WebAssembly, and then you can benefit from 50 engineers who full-time worked on tiered JITs that will run your code super fast. So, if you have a big Coq development, then from time to time you might want to test things or to see, does this evaluate to what I think it should? And this provides a reasonable means to do it. So for example, here, you can check that this is actually what you expect at the end. And indeed, is one odd? Yeah, I think so. So that matches what I would expect. So I've verified that at least this specific thing does what I expect. Okay. So how does it look like inside? So what we've done is basically we've taken CertiCoq and we've hijacked it. So CertiCoq starts from Gallina over there, uses metacoq to get a deeply embedded term, and then does a whole bunch of very clever things to defunctionalize in CPS and God knows what, and do a whole bunch of optimizations. And we don't need to think about these. These have been done by someone else. These have been very nicely encapsulated to generate this lambda ANF terms. And then what we've did is just compile these to WebAssembly and then prove that this compilation is correct. And this was, it's a very nice thing that it just works, that we were just able to take it off the shelf and use it. So now I'll just ramble more about these things. So I'll talk quickly about WebAssembly and why it's nice. I'll talk about CertiCoq and this rather low language inside of CertiCoq that we start from. I'll describe quickly the backend and then some evaluation, because the whole point is it kind of goes a little bit fast. So WebAssembly. What is WebAssembly? It's the promise of almost native performance with secure sandboxing. So you can run a program that someone else has written and it won't destroy all of your data. And one of the very nice things is that it has a simple and clear semantics, because PL people have gone out into industry and sort of pushed for simple, clear, unambiguous, the program will run the same on every single machine semantics. And surprisingly enough, people have listened. It's supported by every major browser, and the same program will run the same everywhere. And this means that you can take your Rust program, your C program, and you don't have to worry about how the hell it's going to be compiled on that platform or that platform. You just compile it to WebAssembly, ship it, and it will run. And it's been very successful on the web with the whole Web3 and blockchain buzzwords. But there's also just normally running normal applications on a browser, and also outside of the browser. So there's standalone runtimes, and WebAssembly, it started with the web, but the web is a bit of a misnomer these days. It's really a general thing. And because it was designed by PL people who knew what they were doing and who really cared about having a precise language, we have a complete specification of the 1.0 standard. It's word for word, but in Isabelle or in Coq, depending which proof assistant you favor. In this room, it might be slightly biased to the right. But the thing is, this is a real language standard that is really used in industry, and we have a complete Coq formalization of it. So, you know, it's a huge success story, and the fact that we were able to use it as a target is really very nice. So what does WebAssembly look like in practice? It looks like this. It's a simple stack language where you define modules. Modules are the sort of unit of shipping code, and then a module can have some global state here, some constant that is initially 41, and then you can define functions. So it's sort of structured. The assembly is a bit of a misnomer. It's something that is easy to generate assembly from, but it still has functions, it still has structured control flow, and then inside of the function is just a simple stack language. So it does exactly what you expect, you know. Const pushes a constant on the stack, and there's no catch, you know. It's not like C. This is actually literally just pushing the constant 1 on the stack. And then the operational semantics, well, this is a little bit of a lie, but it's barely a lie. It's what you would expect, just there's a little bit more details. So there's something about calling the host, which is, I guess, the FFI aspect. I won't talk about that. And then there's a store, which is literally, you know, it's a store like you would expect. So a local variable has a value. There's no tricks. There's no catch. There's memory. Memory is just a list of bytes, and this is what we will use to store the constructors of our Coq term. And then the list of instructions is a stack. It just works like a stack. So everything is completely as expected. So for example, if you have your program here that we had inside our function that starts by pushing the constant 1 on the stack and then gets local variable 0, then, you know, there's just, like, if you look at the standard, there are named rules of the operational semantics, and these are the thing that the web browser implementers pay attention to. So it's exactly like a PL textbook, but it also runs in your browser. So now maybe a quick word about CertiCoq itself. So what we do, as I said, is we take this lambda NF language and we extract WebAssembly from it. And so it means that sort of from the deep embedding down to WebAssembly, this is completely verified. Original CertiCoq from lambda NF generated C-Lite, and I think the proof is sort of almost there, but not quite 100% there. Maybe someone in the audience can correct me since I last checked. So we have, as far as I know, this is the first verified compiler to WebAssembly. What does lambda NF look like? It's a relatively simple lambda calculus, exactly as you'd expect, where you have constructors that takes a bunch of arguments and then pattern matching. And this is basically, you know, if you have successor of something, well, you will just have your successor here, and then if you have some destruct on that, then this will be this case construction. So it's a very simple language. It's very pleasing to work with. Like, it's very nice that CertiCoq has this nice factorization through this. You have a language with variables that are globally unique, so it's easy to compile. There's no primitives. Everything is in CPS, so calls are easy to compile. And the function definitions are pulled out to the outside, so there's none of the nasty Coq nesting. So in a sense, it's very easy to generate WebAssembly code, and this is what we used. So how does our part of the compiler work? So it's basically what Wolfgang did is he looked at the CertiCoq C backend, and he looked at the WebAssembly specification, and he sort of tried to marry the two. And it works just in the way you'd expect. So you have a code-gen function that takes an expression that just recursively builds a WebAssembly program. And because WebAssembly is nice, this just works out of the box. And then you do that for all the functions one by one, and you also generate a few helper things to like, typically you want to look at the output of your function, so there's something that converts the representation in the heap of a Coq term translated to lambda ANF and just prints the S expression. This is what we used earlier to look at the result. And then there's something like you need to store the result somewhere. You can run out of memory in WebAssembly, so you need a little point, like a little flag for that. But apart from that, it's really, you just take the lambda ANF term and you lay it out in the heap with a tag and then the arguments just in the bytes after that. And again, as Ahmed said, you're supposed to show Coq code. So this is the Coq code for the compilation of the projection in lambda ANF. And basically, if you're taking the projection of something, well, you just compile that thing, and then you look up. So you need to do a little bit of arithmetic. So you need to skip the tag and look at which bytes correspond to the thing that you're projecting. But because the memory in WebAssembly is just a flat array, there's no complicated things like in C. It's just arithmetic. So you just need to check that this does the right thing. And then you can try to prove it. So the correctness statement is if you have in Coq some expression that reduces to V, and our compilation function returns a WebAssembly module, then WebAssembly says this little extra step, which is called instantiation, which takes a module which is a sort of static object and produces what is called a store, which is a bit of a confusing name, which is a sort of dynamic state. So you need not just compilation, but instantiation to succeed. Then basically you can run the WebAssembly program, and this is this formal definition of the semantics of WebAssembly. And then if you get an empty stack, then you've terminated, and then the globals in the WebAssembly state sort of are a representation of the value V that you expect at the Coq level. Or you were unlucky, and then you run out of memory. And this is relatively, there's a few side conditions. The variables in E need to be unique. This is easy to implement. The size of everything has to fit in I32s. Otherwise, compilation would need to add. You don't want to have big-ins for everything. So, if you defined 2 to the 64 plus 2 constructors in Coq, then it would be kind of annoying, and we just ignore that. We say, well, no one will do that, and if they do, it's their problem. And there's a few side conditions, but these are very minor. And then the idea of how do you represent lambda ANF / Coq value in WebAssembly is kind of the obvious thing, except there's details everywhere. So there's things like you have to think about offsets in memory, but fundamentally it's doing exactly what you would expect. And the proof is like in a PL textbook. It's by induction on the evaluation derivation, and you just make sure that the thing goes pretty much in lockstep. And you need to define this relation that is, what does it mean to lay an entire lambda ANF term in memory? But it does kind of the obvious thing. I keep saying that, but it shouldn't be seen as a negative thing. The fact that it's obvious is so nice. It's so good. It's such a difference to working with other languages. And then we can think, OK, so now we have this thing. We have this compiler. We know that it's correct, but is it any good? And here so it's, the compiler itself is like under 500 lines of code. It's very, very nice. And the correctness proof is not that long. And then we've ran it. So it's a small compiler. It doesn't try to be very clever, but at least it's verified. And then we've tried it on a few benchmarks that CertiCoq used for itself. So they have this SHA function, which is quite numerically intensive, and they have some decision procedure for separation logic, I think. And I'm now discovering this slide at the same time as you are, because Wolfgang ran it slightly faster this morning, and then I bravely pulled his changes to the slides. So if we compare, so this is CertiCoq itself, which generates C. And if you run it with GCC minus O2, which is very unverified, it's like, let's pick the first example. There's like 7 milliseconds for C, and our thing is 81 milliseconds. So it's like roughly 10 times slower, something like that. This is not a very scientific evaluation. It's just a back-of-the-envelope thing. So it's like, it's not as good as C, but it's still pretty good. And this is after spending not too much time trying to optimize the hell out of everything. We suspect that it can be made even faster. So this is like, it's a very simple compiler, it's verified correct, and it still gives us reasonable performance. So to conclude, I'll maybe talk about the limitations a little bit. There was this step about instantiation that I kind of skipped. We think that we could also prove that instantiation just goes through. We haven't done it yet. I think the big problems right now are sort of performance. Performance both in terms of time that I've just mentioned, but also in terms of memory. So currently, we don't attempt to do any form of garbage collection. So the heap just keeps accumulating old lambda ANF terms that have by now been completely discarded. Logically, but not physically in the heap. One thing that would be kind of nice would be to support sort of primitive types. So currently, if you want to add the number 7 and the number 4, then you need to represent 7 as this giant linked list in the heap, and then 4 as this giant linked list, and then walk over them. And that is kind of completely inefficient. And so we're thinking, how could we try to use like the primitive types of WebAssembly to do if we know the bounds on the integers, or if we don't, at least use an efficient big int representation as opposed to like the world's worst representation of integers. WebAssembly, the 1.0 spec, didn't have tail calls, but it's just a question of once you've generated the binary, you can do this untrusted step of replacing call by tail call. We don't have a formalization of that, but we expect it should be relatively doable. We just don't have it in our formalization. And CertiCoq has several types of terms it can generate, and currently we only support a specific one, but I imagine we could do something slightly nicer. So to conclude, we have a verified WebAssembly backend for CertiCoq. It runs with like okay-ish performance. You can grab it off the internet at this address, and then in the future we'll try to think about GCing and performance. I'm happy to take questions.
Thanks. I think we have some minutes for questions.
Thanks. So I was wondering, on that one slide, you had a fun little footnote saying one benchmark crashed what to Wasm or whatever, something that is, some graph coloring something, because of file size. How big was that file and why was it so big?
It was quite big. I think, I don't remember how big, but it was like maybe a couple of megabytes, something like that. Something like you wouldn't really, I don't think, yeah, it wasn't really a sort of very normal program to write. And I don't remember exactly why it was so weird.
Oh, the couple megabyte binary doesn't seem so terrible either, but okay. Maybe I'm just desensitized by Rust.
I don't remember the details, but I think with loads of these tools, they're sort of, they are designed to handle a specific, you know, they only make it handle the things that they encounter, and I guess this was just a weird program from their perspective. Yeah.
Thanks.
Just a quick observation, because Wolfgang pushed the statistics at 5 in the morning this morning. So could you go back to the slides with the tables?
Yes.
So precisely where you have the cursor, we're actually faster than ComCert on one of the statistics. So I was quite proud that Wolfgang actually achieved this.
I mean, it shows the benefits of, tiered GCs written by hundreds of Google engineers. Not GCs, JITs.
Thanks.
So to add the GC, if you go the route of using the native Wasm GC, which seems maybe the easiest option, do you think it would change your compilation path and code a lot, or do you think it would be like an easy change?
I imagine from the point of view of our compiler, it would change very little. The problem is you would need to change the our formalization of the WebAssembly specification to handle the GC, and currently we haven't looked at that. I think this is one of the challenges with WebAssembly, is that the spec is, people are very keen to add things to it, very, very keen. And it's difficult to keep up.
In this slide, in the performance evaluation, the two versions that you see do have GC, whereas yours doesn't, so you're comparing different things?
Yes, that is correct.
And do you have any idea how much they pay for freeing memory?
No. This is a good point. As I said, it's a very back of the envelope. We haven't done much work on performance, so we're comparing apples and oranges in any case.
Hi, thanks for the nice talk. I was wondering, I mean, there's a lot of very weird things in the Coq front end, and some of them are supported in MetaCoq, some of them are not really supported yet. So I was wondering what kind of nasty things are supported all the way down to WebAssembly, things like, I don't know, co-inductive types or primitive types, or this kind of nasty beasts.
That question is well above my pay grade. You should ask the MetaCoq people.
Yeah, I mean that's why I'm asking, because I know, I mean, I'm from the MetaCoq people, so I know what I know what no, so I know what crazy things we support, but I was kind of wondering if you knew how much of them are supported all the way down through CertiCoq, or whether CertiCoq has to kind of restrict some of the things.
I think there is Mathieu who's raising his hand over there, so maybe he can answer.
I'll ask him then.
No, maybe he should answer.
Or maybe he can answer it.
Wait, I think there's a microphone coming your way.
The primitive types are primitive values are translated down to CertiCoq and down to lambda NF, but not operations. We don't do anything special about int add, for example, for int63 primitives. So you have to implement it in C or in WebAssembly as a FFI library, and there's no proofs about it. And co-fix points are not translated to down to lambda NF. We tried one naive implementation, translation of fixed point down to co-fix points to fixed point. It was a very naive one that copies stuff all the time, but its proof is not so easy, so it was not integrated in the verified pipeline. And the rest of Coq is translated.
I think one of the nice things is because we sort of hijack the CertiCoq pipeline so low that whatever will be done for C, we will sort of inherit for free, I expect.
Do you have an estimate of the size of this project in terms of man-months?
In terms of man-months?
10 ECTS.
Yes, 10 ECTS. Which is literally a number of hours by EU regulations. By law, it is a number of hours.
Yeah, but 10 ECTS for how many people?
One.
One, okay.
Very good too.
Well, because ECTSs are hours, they are fungible between people.
ECTS is 30 hours, not formal.
There you go. Formal semantics of EU regulation. Oh, I think Ralph said how many hours? 30 hours for one ECTS. So you could use a CertiCoq-Wasm to run this multiplication efficiently.
Let's thank Jean again.